Hi, ladies and gentlemen. Rosie and I are here to make another video for you that goes along with the Google Slides that you hopefully have been filling in as we move along through this unit. So, we've talked about fossils and fossil types, and we know that it's not easy for an organism to become a fossil, that the conditions have to be just right. It has to be buried, usually in sediments or some other material, pretty quickly. And if it has harder parts, that definitely will increase its chances. And that these fossils tell us a lot about the Earth's past, that obviously life has gone through a lot of changes. And those fossils can also tell us that, uh, the Earth has gone through a lot of changes, that the continents have moved over time, and the climates have changed over time and all of that. So fossils give us a lot of clues to the past. But the one thing that you may be asking yourselves is okay, we find all of these organisms that no longer exist and we only see fossilized remains, but when did they live? And that's what we're going to focus on today is, how old are these fossils that we find? And we're going to look at it from two different ways. There's what's called relative age, meaning how does uh, one age of one organism relate to the age of another? Which one's older? Which one's younger? But we don't know specifically how old. And then there's absolute age, which we're going to refer to as radiometric age, which we'll talk about later, which gives us a better idea of really how old something is. So, like Rosie here, I know that Rosie's 10 years old. We got her as a puppy, and we know her actual or radiometric age. Now, I have another guest joining us today, and there's Turbo. And Turbo, I really don't know how old Turbo is. I know I've had him more than 10 years, so I know that he's older than Rosie. So I could look at it as a relative age that, hey, Turbo is older than Rosie. I know Rosie's 10. I don't know how old Turbo is, but I can tell you that he is older. I've had him at least 10 years, and he was an adult when he was first given to me. So that's called relative age. How old's Turbo? That's a good question. But we know he's older than Rosie, and that's one way of looking at what's called relative age. And by the way, Turbo says hi. So we're going, as I said, to talk about relative age first. And one way of looking at the relative age in terms of how does one layer of rock or fossils relate to another, what's older, what's younger, is what's called the law of superposition. So, where we live here in western Pennsylvania, you drive down Route 8, you go on to Route 28 and other places, and you see where they cut the hillside out, and you see all those horizontal layers of sedimentary rock. And it makes sense if those sediments have built up over time that the older sediments are going to be on the bottom and younger sediments will be on top. So if we find fossils in any of those layers of sedimentary rock, the ones found farther down, in most cases, are going to be older than the ones found on the top. So if you look at your Google Slides, the first one you're going to see is the law of superposition. And there is a diagram there on the right that shows layers of sedimentary rock and fossils that would be found there. And you can see how they've changed over time. And there are clues as you can see that the shells and other fossils, trilobites and so on, you see at the bottom means it was once a shallow sea, giving us a clue to, there once, there was a sea there and it's gone through a lot of change. And then there you can see there's land organisms closer to the surface. So those seas disappeared, those organisms went extinct, and you see the others. And even on the left, if you look there at the picture of the Grand Canyon and those layers of rock, you can see a lot of layers of sedimentary rock. Limestone giving us a clue there was once a sea there and the organisms that would have lived there. And also a layer of basalt, which is an extrusive igneous rock, meaning lava was there. There was a volcanic eruption in the past. There was once lava that hardened and changed to rock. So on your Google slide, under letter A, you should put that The law of superposition states that in a series of sedimentary rock layers, younger rock layers normally lie. Well, I think you can probably figure it out, but the words you should put in are on top of the older rock, or the older rock layers, yes. So, where under letter A, normally lie on top of older rock layers. And that's what you should fill in there. And that's the law of superposition. Okay, so another way of looking at the relative age of a fossil is what's called index fossils. Just like an index in a book gives us clues to where to find something in a book, index fossils don't tell us exactly when something lived. So they would not give us actual or radiometric age, but give us again a relative age of, hey, we know these organisms existed for a period of time and they went extinct. And they no longer obviously exist, but we have an idea of a span of time when they lived. So if we find them in a layer of sedimentary rock, we can say, hey, we know that this organism lived 500, 600 million years ago. And if we find other fossils alongside it in that rock, we know that rock and those other fossils are in that span of time of maybe 500 to 600 million years ago, or whatever the span of time would be. So they kind of just give us a clue. So if you, there are index fossils for all the spans of time, some we'll talk about later. A really common one from what's called the Paleozoic era and the earlier divisions of it is a trilobite. And I showed you a trilobite earlier, but there's one again. These organisms lived in the shallow seas, even where you live in Hampton at one point, hundreds of millions of years ago. And we can, if we find them, we know that the rock they're found in and any other fossils are from that same period of time. So they're a good index fossil. So on your Google Slides under letter B for index fossils, and you see a chart there of a lot of different index fossils over the different spans of time. For number one, you should put the trilobite. So if you could fill that in on your Google slide, put the word trilobite. Remember, they came in a lot of different sizes or a lot of different species. And if you look at the next slide, I believe, you'll see some really large fossilized remains of trilobites. So that trilobite should be filled in. Okay, so we're now going to move on, and if you're following along on your Google Slides, as you should, we're going to be at letter C and what's called radioactive dating. Unlike the law of superposition and index fossils that we just talked about, which show or just give us a relative age, radioactive dating gives us a more absolute age. It gives us what we call the radiometric age. It's not going to give us an age like that thing's 30,485,712 years old. But hey, when we're talking millions of years, if we can narrow it down to a more specific age, that's going to help us a lot knowing when things existed, when changes in the earth occurred. So rocks and those rocks that contain fossils have very, very, very small amounts of radioactive elements. It's not anything that's going to harm you, so it's not dangerous, but they have very, very small trace amounts of these radioactive elements. And if you remember back, we talked about radiation. There was particle radiation, which we said was different than things like UV radiation and so on. But anyways, so we can measure the amounts of these radioactive elements, and when they go through what's called a decay, not like the decomposition that bacteria does on a leaf or something, but it's called radioactive decay. They change into another element. They break down into other elements. And we know what elements they change to, and we know the rate at which they do so. They do it at a very, very constant rate, which is what is so helpful for us in determining their radiometric age. So, for example, one type of uranium can change to lead. Uranium is symbolized by the letter U, lead by the letters PB. And as I said, they change. It's parent to daughter, actually, the parent element to the daughter element. We know how long it takes for that uranium to change to lead. And when half of the uranium changes to lead, we call that a half-life. Okay, it's the time it takes for half of a radio element to decay into its decay elements or daughters. And you can see that under letter C. And what I'd like you to fill in at letter C is radioactive dating gives us the radiometric age. So if you would write in on the slide with letter C, radioactive dating, the word radiometric, which is a more actual age. It's giving us a more specific age than what we looked at with relative age earlier. Okay, so radiometric. Now, once you have that written in, if you'd move to the next slide, I have something there kind of demonstrating this for you. You can see there's U's for uranium and PB's for lead. And there's other elements they can do this. There's carbon-14 for things that aren't as old and so on. Now, we're going to say that the time it takes for uranium, for half of the uranium to change to lead is a half-life of 1 billion years. So if you started with 30 uraniums, and then when you measure, you know that was the amount you started with, because when you measure that piece of rock or something and you see that there are 15 uranium particles and 15 lead, that means half of it has changed. It's gone through one half-life. So it must be 1 billion years old. And if you look at the bottom left, you see that there's 8 uranium and 22 lead. And that means that of that 15 we had after one half-life, that has another 7 has changed to lead, approximately half. So it's gone through another half-life, and it's 2 billion years old then. And then if you look at the bottom right, where you in the previous one we had 8 uranium, now we only have 4, and you see the ratio of uranium to lead, there's 26 lead. So what that means is it's gone through another half-life, so it must be 3 billion years old. So we started out with the 30. When we saw 1/2 of it was lead now, that's 1 half-life. When we see now that, half of that, so now we're at 1/4 of what we started with, okay? We see that's 2 half-lives, and if you think about, we started with 30, and in the last one, there's only 4, so we have approximately like 1/8 of what we started with in uranium, and the other 7/8 is lead. So it's a little, possibly difficult to grasp, but how many half-lives, knowing the half-life of those elements, we can tell how old something is. Okay? All right, so that is how we find radiometric age through radioactive dating. All right, so as I said, I know that the whole radioactive dating, getting radiometric age can be a little complicated. If you can just get a general idea of what that's about, I'll be satisfied at this point, all things considered. On the very last slide, letter D on conformity, there's nothing you have to write here, but I just want you to know that, again, this doesn't even involve fossils, but when we're looking at those layers of sedimentary rock, and like we said, generally in your one assignment, it had the law of horizontality. They're found in those nice horizontal layers. You may see one that's shifted upward or downward. There's a little bend in the rock, or there's a little bit that's eroded away, or you can see where magma affected it. This just gives us clues to when the Earth went through some changes in the past, and we'll learn about faults and folds another time. But I just want you to kind of get a little idea of what an unconformity is, okay? All right, guys, hope everybody's doing well as always. Stay safe, and we'll be talking again soon.